Hello and welcome. The purpose of this video is to talk through each of the problems that you saw on the key assessment. I'm going to mention where we saw the concept in class and also help you reflect and review for each problem. So question number one. Question number one asked you to simply identify all of these different aspects of atomic structure. We saw this in Unit 1, Day 3 when we looked at the mass and charge of each subatomic particle, so protons, neutrons, and total electrons. We also saw this in day 4 when we worked out the same thing for protons, neutrons, total electrons, and then valence electrons we talked about on day 5. All right, so metal or non-metal, you would have gotten that just from looking at the periodic table and using the color coding. Number of protons, we learned on Unit 1, Day 3, this should have come from atomic number. Number of neutrons, well, number of neutrons, we learned here, protons plus neutrons are equal to the mass number. In this case, this is a slightly unusual version of carbon. There's a mass number of 13, meaning there are 7 neutrons, 13 minus 6. Carbon can also have 6 neutrons and a mass number of 12, but in this case, the mass number, that's the mass of a single atom. This atom that we had happened to have a mass number of 13, so the number of neutrons was 7. I gave you number of total electrons, and so I'm going to do charge first. Charge, we learned, was protons minus electrons, so proton 6 minus 6 equals neutral, or 0. And now let's talk about valence electrons for B. So there were a couple things you could have done here. You could have either looked at number of total electrons, and you could have said, okay, I know there's 6 total electrons. I know that the first energy level must have 2 electrons. That means there must be 4 in the second energy level. Valence means outer shell, and so 4 valence electrons. The other thing you could have done, and many of us wanted to use this periodic table trend, which was great, but you had to mention that this worked because the atom was neutral. This is only true when the atom is neutral. Once you start adding or removing electrons, you're usually trying to reach a full shell, so your number of valence electrons wouldn't work. So in order to get a complete explanation, if you mention the periodic table trends, you also mentioned that I could use this periodic table trend because my atom was neutral, which I saw right here. All right, question 2, part A, macro scale observation. So I was testing 2 things here, the word macro scale and the word observation. Macro scale is what we can see. Many of us remembered that. But if you put anything about atoms or bonds, that would not be macro scale. And then observation. Some people did try to put inferences. You mentioned something like because, or you mentioned you thought the pan was really old. That's an inference. You might have made an observation that the pan had some orange, dark brown color. You might have mentioned that it was round. Anything that you could see with your eyes would have been an acceptable answer there. All right, B, you borrow a light microscope from school to examine the oxidation. You zoom into the size of a cell. Could you see iron oxide at the atomic scale? Well, obviously not. Many of us did say no, which was great. You needed to provide a reason. There were a couple reasons that you could have provided. You could have focused on this idea of light microscope. We know that only electron scanning microscopes can see atoms. And even then, they only see the vaguest outline. You could have focused on the idea that this is the right size for a cell. Remember, we talked about this, that a atom and a cell had the same size difference as a basketball and Vatican City. So atoms and cells, some of you mentioned atoms are smaller than cells. I was looking for you to provide some evidence that atoms are just so much smaller than cells that you can't even compare them. In the same way, you wouldn't just say, oh, a basketball is smaller than a city. Like, yes, they're on a completely different scale of size. So I was looking for you to say no there, and then you might have mentioned something about electron scanning microscopes like we saw in evidence 3 on day 2. You might have mentioned something about how small an atom is. You could have used the blueberry example. You could have used the fist example. So just talking about how small an atom really is, how hard it would be to see at only 400 times zoomed in. You could have also focused on the fact that I told you that it was the right size for a cell. And we know that cells are just a completely different size scale than atoms. All right. C. Explain with one reason why iron oxide is ionic. Well, it's ionic because metal and non-metal. I did not accept there it's ionic because electrons are donated, received. I did not accept that because electrons are donated and received because it's ionic. It's the opposite argument that you need to make. The fact that we have a metal and non-metal leads to electrons being donated or received. If you did the extension, you might have mentioned electronegativity there. That was certainly not required, but if you wanted to bring in the extension, this is where you could have done that. All right, D and E, identify the ion that would form and explain why. All right, so some people wanted to just say I had a negative ion. When we did this in class, when we identified an ion, we identified the formula for the ion. So you were expected to do the same exact thing on the test. Identifying the ion means providing the formula. So not just saying it would be negative or it would be an anion, but actually saying O2 minus. This is the ion that forms, O2 minus. Why does that form? Well, I was looking for you to use this reasoning that we used on day 6. We know that oxygen has 6 valence electrons, 6 valence electrons. The two options would be to lose 6 valence electrons or gain 2 valence electrons in order to reach a full shell. It's easier to gain 2 valence electrons, and so that's why we would gain 2 valence electrons. When we gain 2 valence electrons, we get a charge of 2 minus. So I was looking for you to walk through that reasoning in the same way that we did in these slides here. You might have used our phosphorus example. Phosphorus was one where we got a negative ion because you added electrons. And we gained 3 electrons because that was easier than losing 5 electrons. So I was looking for that full reasoning. This would have been in E. All right, moving right along. F, explain the charge you would expect iron to have. Well, there's a few things you could have looked at here. You could have looked at this information. I told you iron had 2 valence electrons. And we know when you have 2 valence electrons, we saw this on day 6, when I have 2 valence electrons, like in beryllium, I'm going to lose those 2 valence electrons and gain a charge of 2 plus. You also could have said, okay, I know that I'm forming a compound, and I know that compounds are neutral, just like we saw in the ionic bonding day. So you could have said, I already established that I have O2 minus. I know, this was a point that some of us missed, I know that there is one oxygen ion and one iron ion in FeO, because if I have no subscripts, I assume 1. I think some of us made this assumption, but you didn't make your thinking explicit. I can only grade what I see, right? So that's not always the case. I could have K2S, for example, but in this case, I know there's only one of each. So if I have an O2 minus, well, Fe needs to be 2 plus to form a neutral compound. So either of those would have been acceptable. Of course, you could not use the periodic table there because iron is a transition metal. And so because it's a transition metal, you cannot use any of the rules that we learned in the periodic table. All right, G, the conductivity. I'd say the biggest thing that was missed here was that, I'm actually going to go back to the question for a second. The biggest thing that was missed here was what do you expect to observe? Some people said it would conduct electricity. That's an inference. How did I know it was conducting electricity? I would observe the light bulb light up. Some people tried to talk about iron being metallic. I'm not sure where that was coming from because we didn't study metallic bonding at all. We did study ionic compounds, and we worked on, in day 10, we worked on explaining why ionic compounds conduct electricity. So you drew this model as well. We related what we did on day 10 with salt being ionic, sugar being covalent, and then we did some work that day explaining how the ions can split up in an ionic compound, and that's what conducts electricity. So some sort of explanation around being ionic. If I'm ionic, I have charges. If I have charges, I can conduct electricity. That's what I was looking for there. And then the observation was the other key piece to that problem. All right, now finally question 3, methane. So the day that we practiced this was the covalent bonding day. You might have used something like SH2 as a model. Obviously, sulfur is a little bit different than carbon. Notice that we have neutral atoms to start. So that was the biggest thing that I saw people kind of struggling with. So we need to start with neutral atoms. So carbon, we already know what the carbon neutral atom looks like. We've already seen that today. And now hydrogen, I have a neutral hydrogen. Okay, so some of us tried to add a new electron. We don't add a new electron. Notice that sulfur is 1, 2, 3, 4, 5, 6 valence electrons. That's the only valence electrons I show. I did not add any valence electrons. You do need to show circles. That's how we represent shared electrons. Some people tried to do lines or arrows. It is indeed circles. All right. So I see now carbon has 1, 2, 3, 4, 5. Not quite enough. Hydrogen, I'm going to add a new hydrogen. Carbon now has 1, 2, 3, 4, 5, 6. Cool. Each hydrogen has 1, 2. Remember, they're sharing, so the electrons count for both. And that's full for hydrogen because 2 electrons in the first shell. So I'm going to keep adding hydrogens until that carbon atom is full. And now it should indeed be full. 1, 2, 3, 4, 5, 6, 7, 8. And then hydrogen, 1, 2, 1, 2, 1, 2, 1, 2. Each hydrogen has 2 valence electrons. All right. B, so explain the differences at the submicroscopic level. So some people tried to talk about conductivity or melting point. That's not submicroscopic. The things you could have talked about, we saw in day 9, ionic and covalent bonding. So you could have talked about what the electrons were doing. You could have talked about if you have ions or neutral atoms, how atoms were held together, lattice versus other structures. Some people tried to say no structure. There is a structure. We just didn't name any of these structures. The other thing that people said there, which I thought was excellent, was that methane is a gas, and so the particles would be more spread out, whereas, what was the other thing? Iron oxide is a solid, and so the particles would be closer together. You might have gotten that from like a middle school science class, for example, and I thought that was an excellent connection, so I did give a point for that as well. All right, thanks for watching. As always, let me know what questions you have, and have a good day.